Okay, hi everyone. This paper is called A Fast Binary Splitting Approach to Non-Adaptive Group Testing, and it's a joint work with Eric Price. So let me start with a toy example illustrating what group testing is. So imagine we have a bunch of flasks as shown here, and a few of them have some sort of contamination, and we'd like to know which ones do and which ones don't. Okay, you can see because I've colored them, but imagine in advance they all look the same. And we'd like to do some tests to figure out which one is contaminated and which one is not. So the simplest way to do that would be to test all of these one by one. We assume we have some sort of machine that can accept some liquid and perform the test, give the outcome. So we could do them one by one, get all the outcomes. The idea of group testing is that if contamination is very rare, then we can get away with much fewer tests than that. And the idea is simply to group these flasks together, for example, mix a bit of their liquids together and put the mixture in the machine. And by doing that, if there's any contamination among the mixture, we'll get an outcome contaminated. If there's no contamination among the mixture, we'll get a clean result. And that can save tests because, for example, if you look at this second test here, we've just used a single test to figure out that all three of these flasks are clean. So we can immediately rule all of those out. If we get a contaminated result, maybe we'll need some further tests to narrow down exactly which ones are and which ones aren't. But the idea is that if contamination is rare, then we can get away with much fewer tests than one by one. So this was originally proposed for medical testing. And in fact, for obvious reasons, recently, medical testing has been the focus again because it has been used in various countries for testing COVID-19. But it is also more of an abstract problem. It's found use in multiple access communication, databases, and many more. So we're not really focusing on applications. We're looking at the theory of group testing in this talk. Here is a more general picture of what's going on. So we imagine we have a bunch of so-called items. This would be the flasks in the toy example. In medical testing, you might also call these individuals. A small number of the items is what we call defective. And again, in medical testing, maybe we'd use the terminology infected. And then we have this matrix of tests indicating which item is in which test. So each one of these is a test. For example, this first test contains these 3 items. Second test contains these 4 items, and so on. And then by the way, I've just described the idea of mixing these together into a group and testing the whole group. At least in the noiseless setting, all we get is the bitwise or the column-wise OR of these defective items. So these 3 highlighted columns are ORed together and we get the outcomes here. So for example, the OR of these 3 gives a positive outcome. In the second test, there's none of these defectives included, so we get a negative outcome, and so on. And then of course, given the outcomes and given knowledge of the test design, we'd like to recover the status of every item, whether it's defective or non-defective. So mathematically, we imagine this defective set S. We need some sort of bound on its size, so we call it size K, and we're operating typically in the regime where K is much smaller than N being the total number of items. So this is a sparse recovery problem, but a binary one, sort of like a Boolean counterpart to compressed sensing. We're going to focus on the noiseless case in this talk, so we are literally just looking at the OR of these xj. Xj is just indicating whether item j was included in the test, so we take the OR of that over the defective set S. So in layman's terms, it's just saying 1 if there's any defective in the test, and 0 if there's no defectives in the test. In principle, you could have adaptive testing, where you do a test, observe the outcome, and then based on that outcome, choose how to design the next test. I will talk about an adaptive algorithm, but we are looking at non-adaptive algorithms in this talk, meaning basically that this whole matrix has to be designed in advance. So you can't see any test outcomes and then choose the next ones. You have to just design all your tests in advance in one shot. And that does have some significant practical advantages, because if you design them all in advance, then perhaps you can implement them all in parallel. We're going to allow for randomized testing, and we're going to allow for a small error probability. And this is actually a very important distinction in group testing. If you insist on a matrix that has the so-called for all guarantee, meaning it works for any set of defective items up to size K, then your number of tests required is much larger. It's K squared log N typically. If you allow for a small error probability, that goes down to K log N. So the for all versus for each sort of recovery guarantee is very important in group testing. The distinction between the two is very important. And we are focusing on the for each style guarantee where we allow a small error probability. So there's been a fair bit of work on this topic, of course. And most of the work has sort of focused mainly on driving down the number of tests. But recently, there have been studies that have been thinking more and more about decoding time. So perhaps perhaps there could be scenarios where you'd like to really recover your defective set as fast as possible and have as little computation as possible at the decoder. And of course, number of tests, it's obvious why we want to keep that low, because tests may be expensive. So for the works that just worried about number of tests, the decoding time was typically linear or higher in number of items n. So typical might be n times k, where there's n items and k defective items. Or maybe that up to a log factor. And the number of tests is k log n, which is essentially optimal when you have a sublinear sparsity. So I'll talk a bit more about that in a second, but think of k log n as essentially being optimal. And in fact, the lower bound is k log n over k. So as long as k is not too close to n, these two are actually equivalent. So we'll just think about k log n as being the target scaling that we're aiming for. So in terms of reducing the decoding time, actually I should say that the earliest works were on this so-called for all or combinatorial setting, where we have the k squared log n scaling. So a few earlier papers did give sublinear time algorithms, meaning basically polylogarithmic and k log n type runtime for the for all setting. In this table, I'm just focusing on the for each guarantee because that's what we're focusing on in this paper. One of the earliest works was this so-called saffron algorithm, and a similar algorithm also known as grotesque, group testing quick and efficient. Both of these had a log k factor blow up in the number of tests. So they got pretty close, but they didn't get quite down to the optimal number of tests, which is in most regimes k log n. So yeah, they got close and they got a fairly low decoding time, k log n, or depending on how you interpret it, you could even say that the runtime of Saffron is k log k. It basically depends whether you're working with a word RAM type model of computation or not. So yeah, for fair comparison with our work where we're using a word RAM model of computation, we should actually say that the decoding time of Saffron is k log k, if you can sort of read the test outcomes in words and operate on those words in constant time. Then there was a couple of follow-up works that were trying to further drive down the number of tests while keeping the decoding time sublinear. And they did succeed in that. So first of all, this inner log factor was reduced to, I guess, like a log ratio of logs, which could even be a constant depending on the scaling of k. And then this recent paper, bit mixing coding, actually got k log n in all the sparsity regimes. But both of these more recent works had a fair bit higher decoding time, k squared term in BMC and even a k cubed term in this other paper. So in this paper, we managed to get number of tests and decoding time both down to k log n, which is the first result to do this. So essentially it's optimal number of tests, and I don't want to quite say optimal decoding time because, you know, with this word RAM model of computation, in principle, we can get lower, but it's essentially optimal or very close to optimal in terms of both number of tests and decoding time. Getting this result required a different algorithmic approach. So we're departing from the previous techniques, which were typically based on either code concatenation or some sort of bit masking idea where you explicitly encode the indices of items into the test matrix. We're departing from all these techniques using a binary splitting approach. And to motivate this binary splitting approach, I'd like to give you what you could think of as like a gold standard adaptive group testing algorithm, which has actually been around since the 1970s. So now we're thinking adaptively, where we can perform a test, observe its outcome, and then choose how to pick the next test. So just very briefly, even in the adaptive case, we can give a very simple k log n over k bound on the number of tests required. And the simple argument behind that is that if we have t tests, then there's only 2 to the power of t possible outcomes, because each test outcome is binary. But the number of defective sets of size k is n choose k. So basically, if we compare this 2 to the power of t against n choose k, then we better have n at least log of n choose k, which simplifies to k log n over k if we think of k as being much smaller than n. So this adaptive algorithm, going back to 1972 by Huang, actually matches that in the sublinear regime whenever k is little o over n. And in fact, it does it with zero error probability. I said that zero error probability requires more tests, but that's in the non-adaptive test setting. In the adaptive setting, we can get down to zero error probability. Okay, so here's the idea. First, let's group the items into k sets of size n over k. So that can be an arbitrary grouping. Then we work through these one by one, work through the groups. We test the whole group. If it's non-defective, we can stop straight away. We know that there's no defectives there. But then if it's defective, then we do some recursive splitting to try to narrow it down to one defective item. So perhaps we test the left half, it comes out non-defective. So that means there must have been a defective in the right half. Then we split again, split in half, test the left half, it's defective, so we further recurse. If we do this enough times, we'll get down to just one defective item. Then we can sort of save that and remove it. And then you may realize, there may have actually been some more defective items. So for example, we didn't test the right half here. There may have been more defective items here. So how should we handle that? The idea is to just take this item, remove it from all further consideration, and then go back to the start. So we go back to this group and test it all again. We do this splitting and we get maybe another defective item. And then eventually we'll do the whole testing. We'll do this step one again, and it'll be non-defective, so we'll know we can stop. So we repeat that for every group. The splitting procedure takes log n over k times, and we basically need to do it k times once per defective. So up to some insignificant second order terms, the number of tests is k log n over k, which matches the lower bound. Okay, so we basically take this idea and turn it into a non-adaptive algorithm. So that sounds a bit tricky because this is really an adaptive procedure. We're looking at the test outcome and we're really using that test item to choose what to test next. So how can we avoid that? So first of all, let me group the items in a recursive manner, sort of similar to what we just saw, but doing it with all the items. So this level 0 I've drawn here is trivial. It's just a set of all items. I'm going to split that in half and form 2 groups, split those in half and form 4 groups, and so on and so forth, down to this final level where I just have individual items. And I could also represent that as a tree. So this tree is just this set of all nodes. Its 2 children represent half each, and then its 4 children represent the quarters, and so on. So this tree representation will be very useful. And you'll notice we have these sort of defective branches going from the root down to leaves. And whenever, it's pretty easy to understand that due to this recursive structure, whenever any node is defective, meaning it contains at least one defective item in its set, all of its ancestors must be defective as well. So we have this sort of rooted subtree, which is defective. Okay, so how do we design the tests? We're actually going to do it in 2 so-called batches. I don't want to call them stages because stages brings up the sort of adaptive style thinking, and this is a non-adaptive algorithm. So I'll call these batches. The main sort of ideas are in the first batch. And the idea is to look at these groups. We don't really want to look at the very top groups because they're definitely going to come out defective. So we can sort of skip the first couple of groups and start at level log k and work all the way down to the last level. And for each of those levels, we randomly place every node into one single test. So by placing a node in a test, remember a node is a collection of items. So by placing a node in a test, I mean placing all of those items into the test simultaneously. So we randomly place each node into one test, and at each level, we've got order k tests to choose from, and we're choosing one of those uniformly at random. Okay, so because we're working from log k down to log n, and we have this sort of binary splitting structure, the number of levels we're using is log n over k. So our total number of tests in this batch will be k log n over k, which is sounding good. It's the scaling that we want. And then how do we decode? So how do we sort of use those test outcomes and extract knowledge from them to try to figure out which items are defective, we use a simple idea of keeping a list of possible defectives. So if a node is placed in a negative test, then we immediately know that every one of its items is non-defective. So if a node's in a negative test, we can just get rid of it, discard it, and we know it's safe to get rid of. If a node's in a positive test, then there's two possible ways that could happen. First of all, if the node was actually defective, then it will always be placed in a positive test because that's the nature of the group testing model. But if a node was non-defective, then it could have still been placed in a positive test because it could have been placed in a test, in the same test as a defective node. Okay, so defectives will definitely be shown as defective. Non-defectives, it could go either way. So that's why we call it possible defectives. The possible defectives will contain all defective nodes plus possibly a few non-defective nodes. But the idea is we can keep control of how many non-defectives are retained. Okay, so the key claims, I've sort of just already said this. By the final level, all the defective items will still remain because we never discard a defective node. Defective nodes are always in positive tests. And we claim that there's at most order k non-defectives with high probability by the final level. So essentially, by doing this procedure recursively, we work down the tree, we sort of discard some nodes. By recursing down in this way, we're likely to not keep too many non-defectives in the possible defective list. And we also showed that the total number of nodes visited is order k log n over k. And this will be important for characterizing our decoding time. I should mention that there was essentially the same idea was proposed in this concurrent work, Cherajki and Marcos. So yeah, they gave a few interesting further perspectives on this. They showed it could give you a for all style list recovery guarantee, and they applied it to several other problems, including heavy hitters and compressed sensing. So yeah, that's also worth checking out. In our paper, we discussed some minor advantages of our analysis, but yeah, overall, I think both papers are definitely worth looking at. Okay, so let me talk about this second batch of tests. So by what I've just described, after the first batch, we have a bunch of mostly discarded non-defectives. We have our defectives, which are all retained. But then we have a few so-called possible defectives, which are actually non-defective. And we still need to somehow resolve that remaining uncertainty to have just the defectives remaining. Okay, so let's discard the items which are discarded. Let's get rid of them in this picture and just look at this. So the idea is now we have order k items with k defectives, and we could do a bit of further testing to resolve that remaining uncertainty. Essentially, all we have to do is randomly do a bit of random testing, and putting order log k random placements into some sub batches of length 2k each turns out to be enough. And that gives you a total of order k log k tests to resolve this remaining uncertainty. Analyzing this step is actually completely standard. It's been done all over the place. It's related to Bloom testing. So this part is very standard. The first batch is not so standard. Okay, and although I might have described the algorithm to make it sound a little bit adaptive, I should say that all the tests are completely non-adaptive in the way the testing is performed. Okay, so a quick outline of a bit more details of the analysis. If we have ck, remember I said order k tests per level, so let's explicitly call it c times k. It's a simple union bound to say that the probability of a non-defective being placed in a positive test is at most 1 over c. Because it's sort of 1 over c k times the number of defectives k, so it becomes 1 over c. And we can basically think of once we're down to a non-defective part of the tree, it's going to continue via a branching process. So the defective branches will definitely continue, but eventually we'll get down to these non-defective branches, which I've shown in blue. And then we could think of those branches as continuing with probability 1 over c, which we think of as being fairly small, maybe 1% or 10%, something like that. So with probability at most 1 over c, 2 children are created. With probability 1 minus that, the node gets discarded. And there's a nice theory about branching processes which we can borrow from to characterize how many nodes are visited. And we can also use a recursive argument to argue how many leaf nodes remain at the end with high probability. Okay, so in fact, if you don't care about high probability, if you just care about the average, then it's very easy to characterize. But to turn this into a high probability bound, we need a bit more effort. We need to show some sub-exponential concentration, and the details of that are in the paper. So like I said, batch 2 is very well studied. We can borrow some previous analyses. Previous analyses typically used the whole set of n items, which would give us k log n tests, but omega n runtime. So by having narrowed down to a small list at the end, we can keep the runtime a lot smaller. Okay, so that was a bit of an outline of the analysis. I've talked about number of tests, and I've talked about decoding time. The naive way to implement what I've just said would be to have sort of independent, so-called fully independent hashes. So essentially, literally placing everything in a uniformly random test. The problem is that that could require a fair bit of storage. Basically, your storage could, again, be higher than linear in the number of items. The good news is that we can replace all of those uniformly random independent hashes by low storage versions with limited independence and still get a very similar result. Okay, so previously we were saying just randomly place into a single test uniformly at random independently. But we can do this in a low storage way by just using a hash function and use our favorite low storage hash family. And with that, we get a similar main result. We show that basically order log k wise independence is enough. So you definitely don't have to have full independence. We believe possibly you could even get down to order 1 wise independence, but we haven't been able to prove that. We've only been able to prove order log wise. And then number of tests stays optimal, k log n. The decoding time depends on the hash family, but it's the query time for a hash times k log n. And the storage basically incurs a storage per hash times log n factor. Here we've just specified that to the special case of Carter-Wegman, but of course there's more modern hash families as well, which could get a different trade-off of the time and the storage. Okay, so the analysis here is similar, but we need to be a bit more careful because we don't have full independence, and the details are again in the paper. Here is again the summary of existing results and our result, where the first, or I should say equal first in light of this concurrent work, to get the simultaneous k log n number of tests and decoding time. And we can also get low storage by using hash families instead of full independence. So a couple of questions for future work. Firstly, could we use order 1 wise independent hashes instead of order log k wise? And we have some progress in applying this to a noisy setting. In fact, this concurrent work applied it to the case of false positives only or false negatives only. And yeah, we also have some results, but not in this paper, for different types of noisy settings where these ideas can also be used, with a slight increase in the decoding time. Okay, so here are some references, and I'll end it there. Thank you for watching.